The photoelectric effect occurs when light shines on a material and causes it to emit electrons. This phenomenon provided the first major evidence that light behaves not just as a wave, but as a stream of discrete particles called photons. Each individual photon carries a specific amount of energy determined by its frequency. The energy, E, is equal to Planck's constant, h, multiplied by the frequency of the light, f. To escape the metal, an electron must overcome a binding energy called the work function, denoted by the symbol phi. This is the minimum energy required to knock an electron loose from the surface. If the incoming light's frequency is below the threshold frequency, f0, no electrons will be emitted, no matter how bright the light is. The individual photons simply don't have enough energy to break the bonds. When a photon with sufficient energy hits an electron, it transfers all its energy instantly. The electron is ejected from the metal and is then referred to as a photoelectron. According to the law of conservation of energy, the energy of the photon equals the work function plus the maximum kinetic energy of the emitted electron. Any leftover energy after the escape becomes motion. Increasing the intensity of the light means sending more photons per second. This results in more electrons being ejected, but it does not increase the speed or kinetic energy of the individual electrons. To increase the kinetic energy of the photoelectrons, you must increase the frequency of the light. For example, violet light will eject electrons with more speed than blue light because its photons carry more energy. In a laboratory, this is measured using a vacuum tube. Light hits the cathode, and the emitted electrons travel to the anode, creating a measurable electric current that we can analyze. By applying a reverse voltage, we can find that stopping potential, which is the exact voltage needed to stop even the fastest electrons. This allows us to calculate their maximum kinetic energy precisely. To summarize, the photoelectric effect proves light is quantized into photons. The energy of these photons depends on frequency, and the process is an instantaneous one-to-one interaction between particles. This discovery earned Albert Einstein the Nobel Prize and laid the foundation for quantum mechanics. Understanding the photoelectric effect is essential for modern technology like solar cells and sensors. Generated by Vision Solve AI.